I wanted to go through an example of using a spreadsheet program to integrate NIST data. So imagine that we're given the following expression for the change in specific entropy for an ideal gas. There's this integral, the integral from T1 to T2 of Cp dt over T. And if you recall, a standard way of solving it that we know about, if Cp varies with temperature over the temperature range under consideration, you have to use these S degree things in the back of the textbook. Well, of course, that's not the only way to do it, and somebody at some point had to compute the value of S degree as a function, so we're going to figure out how to use data to compute this integral. I'm going to pick nitrogen as our ideal gas, and let's actually get rid of that rightmost term to avoid any confusion. Let's pick a situation where we have a constant pressure of 2.0 bar. That means that in going from state 1 to state 2, the rightmost term goes to 0, right? Because P2 over P1 is 1, the ln of 1 is 0. So we can just erase that rightmost term and deal with this. What I want to do is to show you how to use the spreadsheet program to compute the integral itself. And then the nice thing is we can also use NIST data to compare the result of our integration with the difference between S2 and S1, make sure that we're doing a good job, that we're actually accurately integrating this function. Okay, so let's consider a range from 300 Kelvin to 600 Kelvin. And we're going to use NIST data, so as always, I'll give the citation. That's the website we use it from. Okay, let's fire up our computer and bring up the website and go. Now, all of you know how to access the NIST website. The point of this part of the tutorial is just to make sure that you make one important choice while downloading this data. So here's the website. We'll pick nitrogen, and we'll work in kelvins, fine. Let's change to bar, kilograms per cubic meter, and kilojoules per kilogram, okay? We'll pick isobaric properties here because we want a fixed pressure, and that pressure is going to be 2.0 bar. Enter that in there. Low temperature was 300 Kelvin. High temperature was 600 Kelvin. And we'll pick an increment of 1 Kelvin for now. We'll see how that choice affects things later. Now here's the change. Let's pick 10 digits being displayed in our tables. That way, when we do derivations based on the data, we'll have as much accuracy as we think we need. Okay, so I'm not interested in the density, but let's go down to Cp as a function of temperature. So you can already see that it curves a lot. If you go from one endpoint, trace down all the way to the other endpoint, a straight line would not capture the character of this curve very well. So that's why we have to use numerical integration. It's curving. If it was a straight line, we could easily just interpolate. So if we look at the data in a table, one thing we should confirm is to make sure that we're dealing with a vapor here. If we had a phase change in the middle of our Cp range, that could potentially be bad. Cp should usually vary very smoothly as a function of temperature, but if suddenly you had a vapor that turned into a liquid, you might expect a change. Okay, that's fine. So now here's our data, and we're just going to save as. You know how to do this step. So I'm saving this as a text file, and I'm going to go ahead and load it into Google Sheets without you having to watch all of those steps. We've done that before in previous tutorials. So now let's skip ahead and open it up in Google Sheets. And what I've done before we really get underway is also to delete any extraneous columns. So all we need is temperature. We don't actually need pressure, but I listed it. Entropy for comparison at the end, and Cp. So our integral will just involve Cp and temperature. Before we proceed, I do encourage you to look at your lecture notes. That's where I provide the logic behind numerical integration and the analytic form that we're about to type into the sheet. The video tutorial is meant to supplement that to show you what you actually type into the cells to accomplish this. Okay. Our first step is going to be just to compute delta T for each row, so namely the difference in temperature between the row ahead of the one we're in and the row that we're in. Now you might say that's ridiculous, obviously it's 1 Kelvin in all cases. Well, that's true for this data set. But two things could happen. One is you could download a data set with a different temperature resolution, suddenly it wouldn't be 1 Kelvin anymore. The second thing is, depending on where you got your data, maybe you would get a non-uniform temperature interval, and then you would need to compute it every single step. So this is good practice. Let's go ahead and compute it. Okay, so we're creating a new column here, and we'll just call this column delta T. And the column will always involve the temperature in the row ahead of us minus the temperature of the row that we're in. So delta T, so the formula is just equals, and then we go over and select the temperature in the row ahead of us minus the temperature of the row we're in, hit enter, and of course it's 1 Kelvin as predicted. That makes sense, it's 1 Kelvin all the time. Okay, so now we'll drag this down to propagate it through the rest of the rows that we have here, and it'll be 1 Kelvin every time, except for the last row. What's special about the last row? The last row doesn't have a row ahead of it. So we actually need to delete that last entry, the one that currently says minus 600. It doesn't make sense to compute a delta T for that. We won't be computing an area there. all of the area will be accounted for in the rows where we've actually defined a proper delta t. Okay, so now the next step is going to be to actually construct an area for each of our temperature values. And how do we do this? Well, ultimately, it's basically the average of Cp over T times delta T. So the 1/2 times delta T times now Cp over T for the row ahead of us. So this will be the Cp value. We'll enter that in. And then we'll divide by temperature, again in the row ahead of us. And then add Cp divided by T for the row we're in. And remember, I said this was an average. The 1/2 out front takes care of the average aspect of this. So we've got 1/2, that's delta T. Then we just have the other two terms, which are Cp over T for the row ahead of us, plus Cp over T for our row. Hit enter, and we'll get some value for the area. Now we don't know whether or not this makes sense yet, but let's propagate it through to get the areas at each of these temperatures. And again, we have to skip the very last row. It doesn't make any sense. We don't have a delta T. Okay. So we've done that. How do we assess whether or not what we just did makes sense? Well, first off, we haven't really done the integral. To do the integral, we have to add up all of these areas, right? We just constructed discrete trapezoids. Now we need to add up all the trapezoids. So I'm going to put a function here that's just the sum of all of the areas that we just explicitly computed. So I'll range it from there all the way to the last valid entry here, which is the second to last row, if I can find it. There it is. Okay. So that sum comes out to be some number 0.72888. Okay. Now how do we know if this is a realistic value? The claim is that's the value of the integral, so for our problem that should be the difference in specific entropy. But we can compute the difference in specific entropy between the two extreme temperatures just by taking the difference in entropy here, and it's in joules per gram Kelvin. Remember, that's the same as kilojoules per kilogram Kelvin. So let's take the last value down there and subtract off the first value at the very top, up there. What does that come out to be? Well, it's 0.72888. So you can see these numbers compare very well out to about the 5th digit. After that, you start to have differences. Okay, so actually, as far as comparisons go, that's pretty good. We just did a numerical integration where we found exactly the value we would have found to 5 significant digits if we had used just lookup tables. I consider that to be pretty good progress. So now, what if we didn't have the option of looking at the entropy independently, and we just wanted to know whether we expected our numerical integral to be accurate? Well, thankfully, there's a way that we can tackle that too. What I did was, I downloaded the nitrogen data again, but I picked a different temperature interval, because what you could imagine would introduce error into our calculation is the fact that we picked a temperature interval of 1 Kelvin all the time. What if we had introduced finer temperature resolution? So what if we had picked a temperature interval of 0.5 Kelvin? Well, let's try it. So I downloaded data for 0.5 Kelvin, and so in this data set, I already did all of the work, I just want to show you the results. Sure enough, you can see the temperatures differ from row to row by 0.5 Kelvin. Our delta T values are now 0.5 Kelvin all the time. The values of the areas have changed, but of course now there's twice as many of them too. We subdivided our temperature range. So the sum of areas ends up giving about the same number, and 1, 2, 3, 4, 5, 6 significant digits match. So we differ on the 7th significant digit by doing a numerical integration as compared to just taking the difference in the listed entropy values. This is a great way to test to see whether your numerical integral is likely to be accurate. If you change the resolution over which you're stepping, in this case in temperature, and your answer does not change in an appreciable way, or at least a way you care about, generally we're not tracking numbers out to sort of 6 significant digits, that tells you that your integral has converged. So the term converged just means you don't have to worry about inaccuracies introduced by having too sparsely sampled your data set. Looks like we've got that covered, no problem. So we matched the difference in entropy, our integral is accurate physically. We've converged, that means our integral is accurate numerically. Seems like this is a great way to construct numerical integrals. And of course you can do this for any integral where you need data. It doesn't always have to be the integral of Cp dt over t.